Hello all, welcome to the Linux Rootkits for Red Blue Teams course on Pentester Academy. Now in this video, we'll begin exploring some of the internal data structures within the kernel. And in this specific video, we will look at the data structure where all the process information is there, and we will extract some items like the TGID, PID, and the parent process for a given one. Okay, so why is getting the process information so important from a rootkit perspective? Now, as all of us know, processes pretty much, run the system, right? They're responsible for doing different tasks, and that is really what defines a running system. And hence, understanding how they work, how processes are internally represented in kernel data structures, allows us a full understanding of how we can view, modify them, and mangle them. Okay, now before we look at actual code, let me give you a very high level view of how processes in the user space relate with something called tasks in the kernel space. So in the user space, we are aware that we have a process. Typically, the process has its own virtual memory container, and inside that the process runs. Now the main thread, so in C when we define the main function, the very first thread which runs inside the process is the main thread. Now depending on what the process does, it may during its lifetime spawn other child threads, which in turn of course can also spawn further threads. So this is how a process looks like in user space, right? So in kernel space, it's actually a bit different. So in kernel space, we don't treat this process container as a single unit. Rather, we end up treating each of these threads as a single unit. So internally inside the kernel, each of these threads are really represented by individual task structures. So the kernel maintains a list of tasks, and inside that, each of these threads end up being one of the tasks. So we can see that the main thread is a task here, and each of the child threads are also tasks. And in this task list, of course, there are other tasks corresponding to other processes, or even pure kernel threads which are running within the kernel. Now, there are some subtle differences we would have to understand between user space and kernel space processes before moving forward. So what are they? Now, in user space processes, we typically know the process can only access its own virtual memory, right? The most typical case. Now, in kernel space, it is the wild, wild west. So kernel tasks can pretty much access any memory in kernel space. And this, of course, as you can imagine, brings up other complications. So in user space, because every process is typically constrained to its own virtual memory container, it is very, very difficult, if not impossible, for it to corrupt other processes, right? The only way, of course, if you have a process which has high privilege and then it can start debugging other processes and doing other things, right? Apart from that case, it is impossible. Now in kernel space, because any kernel task which is running has access to all kernel memory, kernel tasks can end up reading, modifying, and unfortunately at times corrupting any memory location. Now, once kernel memory has been corrupted, unfortunately, the kernel is actually going to crash because now the state is incoherent and definitely undefined, right? We really don't know what else has been modified and corrupted. Now, this is very, very important because when you're writing kernel modules, you have to be very, very careful, because if you do end up correcting something critical, the kernel will crash. Now, after that, in user space, we know that the process identifier identifies each process uniquely, right? So in a system, you have processes, each of which have unique PIDs for their lifetimes. Now in kernel space, the kernel tasks actually have two different IDs. One of them is called TGID, which is the thread group identifier, and I'll come to that in just a bit. And the other is the PID, which identifies the task ID. So the important thing to realize is in user space, if you have a process with multiple threads, in user space, that process has a specific PID and each of the threads has a thread ID. Now in kernel space, we know that each of the threads, including the main thread, is defined as a task, right? Now each of these tasks have a TGID and a PID. And I'll explain what that is in this diagram and we'll go back. So as an example, let's say we have a process and in user space, it has a PID 100. Now, inside the process, we have the main thread. And of course, the main thread is also going to have a PID of 100, right? Basically within the process, followed by child threads. Now in kernel space, all threads belonging to the same user space process end up having a common TGID or thread group ID. And this thread group ID really corresponds to the main thread, right? Or the first thread which ended up spawning other threads. So in kernel space, what we would find is for the main thread, the TGID would be 100, which would map basically the user space PID. And in kernel space, there is another quantity called PID, which is the task ID. And for the main thread, of course, TGID and PID are going to be same. Now, when we move on to the child thread inside the kernel, the child task is going to have the TGID of 100 because this references the main thread's identifier, right? The thread group identifier. While the PID is actually going to change to some other value. So let's say the PID for this child thread is 200, while this child thread could be 300 as an example. Now this is important to note, and a lot of times you may end up confusing the user space PID with the kernel space PID, right? Now there are further complications possible with something called namespaces, but we will leave it out for now. So the important thing to note is when we are looking at kernel tasks, we will have two IDs. One is the TGID or the thread group identifier corresponding to the main thread, followed by the PID, which is the task ID really, and that would be same for the main thread, which is the TGID would be equal to PID. And for each of the child threads, that would be a unique value. Okay. So apart from that, in user space, well, the interfaces are well documented. The APIs, libc, etc. are very well documented. And the reason this is possible is the libc interface rarely is going to change, right? The internal mechanisms may change. What the system call does in the kernel may change, but the user space API typically never changes. Unfortunately, in kernel mode, this is not true at all. In kernel mode, anything and everything can change, and back compatibility is something which is frowned upon. So Linus Torvalds, the creator of Linux, himself popularly said on the mailing list that, back compatibility is something we don't care about, and we aren't going to make any effort for it, because really what we want to focus on is a really small, powerful, fast kernel, right? And it does make sense because a lot of times an internal working of an operating system needs to have that flexibility that it can move on to better code bases rather than still trying to make everything work from a legacy perspective. So what this means is you may actually, between versions of Linux, especially major versions, you may actually find newer things getting added and older things getting removed. And this means code is your only documentation at times. Apart from that, in user space, it's actually very easy to work with memory, very easy to dump and view memory, view data structures and whatnot. In kernel space, we have to at times make sure that we are acquiring locks before we view or modify memory locations. And we look at this when we actually come to examples. Okay, so we've talked about the overall mechanism. So now let's try and understand the top level structure responsible for defining a task. And this structure is called task underscore struct. And this is the big daddy of all structures, right? So as I mentioned, this defines everything related to a task. It is very complicated, and internally it actually has pointers to a gazillion other structures. Now, as far as documentation is concerned, as I said, most of the times code is documentation. You at times may have to look at the kernel mailing list, and when a certain patch was submitted to enable, maybe a new structure member or a new feature, you may have to look at that discussion and try and understand how it all works. Apart from that, at times, if you're lucky, there may be external articles on LWN and other websites written by some of the core developers working on that feature. Now, task underscore struct is actually very, very important for us from a rootkit perspective, because this is probably the first structure, as soon as the rootkit gets loaded, is going to view and try to modify either for itself or other processes. So let's jump right in. Okay. So let's actually first look at the task underscore structure. So I'm going to go inside Linux 4.6.17. Then I'm going to open up a file called include linux shed.h. You can search for struct task underscore struct, and there it is, right? So this is the core structure, and any task in the kernel is actually represented by this structure. So when we talked about a user space process with multiple threads, the main thread has a task struct. Each of the child threads will also have their own task structs. And inside the kernel, this is the core structure. So from a kernel's perspective, it isn't really looking at processes as the unit, but rather tasks as the unit. Now, there are a lot of different substructures inside this. And again, as I said, this is basically the 4.x kernel. You can well imagine how complicated things could be in here, especially in such a core structure. So I will actually be picking up some of the more important members, especially the ones which may have a bearing from a security perspective for this course, right? So I'll not be looking at every single member. And again, it might not be possible then. Okay, so the first thing I want to actually go ahead and look at is the PID and the TGID of individual tasks. So if we actually scroll down, we see we have two members, PID and TGID. So as I mentioned, TGID is the thread group ID, and PID is actually going to be the process identifier or the specific task ID. Now, we would like to print both of these for a given process. So let me go back in here. Now you can look at the source code under the directory 06 process info basics. Okay. And here is my main file. Now the main file is really extrapolated from the previous example, which is 005. And what I've done is I've made sure that now we take an input called process underscore ID, and this is nothing but an integer. And this is where the user inserting the module can actually feed us a process ID. Now, inside the init function, I basically call a function where I am actually sending it the process ID, which the user entered, and I'm getting back a pointer to this task structure, right? So I've actually defined a pointer to the task structure, target process, and this is what I get back. Now after that, I'm actually checking whether the pointer is null, was there an error, and if of course everything was okay, then I start printing out some of the process details. So I actually called two other functions, print task PID details, and this will print out the PID, TGID, and the binary. And similarly, I'm actually printing out the parent details. Now these three functions, get task struct by PID, print task PID details, and print task parent PID details, are not available as part of the core kernel APIs. So this is something which we have written, and I'll show you how this code looks like in just a bit. Now if for some reason we were not able to find a task struct corresponding to the process ID the user sent, then all we do is we throw an error and we return minus e inval or invalid value. And what happens is that we get back an error when we are loading the kernel module, and automatically the module gets kind of unloaded. It can't be loaded, right? Because there was an error in the init function. Now this is helpful, in case we enter a process ID which doesn't exist on the system. Now the exit routine is just simple. All we do is print exit. Okay. So now let's actually look at these functions and see what is inside. So there is another file here called processlibrary.h, and my idea is that in the next couple of videos we'll keep adding more and more functions. So if required, you can actually use this processlibrary.h in your own projects later. Okay. So I've defined a simple macro here for pointer check. Now let's look at the very first function. So get task struct by PID, and here it is. And what I've done is internally I actually call a function called find vPID or virtual PID for the user supplied PID, and then I call a kernel API called PID underscore task, which actually goes ahead and gives me back the pointer to the corresponding task structure for the given PID. Great. Now after I get back that pointer structure, I actually call another function called print task PID details with that task structure pointer, which is what I've defined here. And internally, what I do is I print the TGID, the PID, and something called the com. So let's look at what com is. It's actually oh, there it was. So here it is. So basically it says that this is the executable name excluding path. Now, as you can clearly see, this has a size limit, and this size limit is fairly small. I don't know if it's defined in this file itself. There it is. It's actually just 16 bytes, and as you can imagine, that's not much to print out binary names, right? The executable name. So you will actually find for larger executables, there will be truncation. Now, how do you find the executable path? I'm going to take that up in a later video, right? But just so you know, when we do print out the task binary, there is a possibility it may be truncated. And after that, we print out the TGID and the PID. Okay. Okay. So then we also have print task parent PID details. Now, if you look at structure here, so if you notice, we have two structures here. Both of them again are task underscore structs, pointers to them. One is the real parent and the parent. So looks like there is an apparent confusion of who the parent is for Linux tasks, right? So the real parent is really the process which went ahead and started this process. And if that process still exists and it's still running, then the real parent ends up pointing to the task structure of that process. Now, if the process which started it exited, then the real parent points to the init process, which is PID1, which is really the first process which starts, in user space. Now, parent is a bit different. In most general cases, parent would be real parent. But in some cases, for example, let's say if this process is actually being debugged using ptrace by another process, then that process needs to be signaled, when this process exits. So for those purposes, then parent would actually point to the process which is actually having a ptrace on this process. So what we'll do is all we care about is the real parent at this point. I'm not trying to see if this process is being debugged or not, etc. So I'm going to be using real parent. And again, this is a task underscore struct, so which makes our life very, very simple from an API perspective. So all we have to do is to find the parent, we take the original task structure, take the real parent, and then after that, similarly, just print com, tgid, and PID, right? Simply because real parent is also a task underscore struct, right? Now, a lot of times, one thing I forgot to mention is people like calling the task underscore struct as the process descriptor, okay? Just keep that in mind. Okay, so now that we've printed all of this and we've looked at these functions, let's compile this code and run it. So I'm going to do a make here. Just going to make sure I do not have this already running. Okay, great. So the first thing we can actually try, let's also open up the source code, is I mentioned that if we give a wrong process ID, which doesn't exist on the system, invalid is actually sent back and the module would refuse to load, right? So let's actually check this first. So I'm going to do a sudo insmod pinfo.ko, and this is the input parameter, and I'm, let's say, going to give a process ID of 0, something I know doesn't exist. And if you notice, it immediately gives us this little error saying invalid parameters, right? Which is, it refuses to kind of load the module and pretty much just unloads it. So now let's actually find a real process. So before that, I'm just going to do a sudo dmessage and clear the messages so that dmessage is clean. So let's do psax. So I can actually see that the SSH daemon is running. 3935 followed by 4000, which is another SSH daemon, right? So my suspicion is this is actually the real daemon, and this is probably another child process which was created by the daemon, where basically I'm connected to over PTS2. So that's a possibility. So let's actually use 3935 and see what happens. I'm going to say 3935, okay? Okay, let's actually do a dmessage now. Okay. So this tells us that the task, the process ID received was 3935. The task binary is SSHD, very good. Of course, it's a very small name. The thread group ID is 3935, which is the parent thread. The PID is 3935, which is going to be true because we are currently looking at basically all the main threads. Now the parent in this case, it actually says is also SSHD, the binary, which means the binary probably recreated and did a fork or an exec or something. And the TGID of this is 1576. So if we scroll up, we should be able to find a 1576 somewhere. Or maybe it may have even exited. Okay, no. Here it is, right? SSHD-D. Maybe the -D is really to demonize it. And this in turn ended up creating this guy here. So I'm curious, what about this guy, right? SSHD Vivek at PTS1 3610. So let's try this. So I'm going to go ahead, remove pinfo first. So 4000 is the PID, right? Let's run dmessage again. Here it is. Okay. This is the task, and the parent is basically 3935 as expected, right? Fantastic. Now let's actually do a PS. Now I'm running multiple terminals, so I really don't know which one, this actually corresponds to. But this bash over here, given this is PTS2, this bash over here must actually be started by an SSHD process, right? Which means the parent of this is going to be an SSHD process. And of course, if I look at the PIDs and the fact that this is PTS2, and that is what we found here, PTS2, this one here, we would probably end up getting 4000 as the parent process for this bash. Let's try that out. So I'm going to remove this once again. I'm going to put 4001, type in dmessage, oops. And there you go. The binary is bash, and clearly, if you notice, the parent is SSHD, and this has TGID 4000, PID 4000. Fantastic. So we can clearly see that the parent-child relationship can be extracted. Now in a later demo where we have a multi-threaded program, I'll actually show you how for a multi-threaded program, all the threads would end up having the same TGID, but a different PID, okay? Apart from the main thread, which would end up having the same TGID and the PID, okay? Fantastic. So this is basically what I had in mind for this video. And of course, this was a long one, but guys, this is a difficult topic, and I really want to at least cover some of the more important stuff together rather than breaking it up into too many videos. Download the code, compile it, try it out. If you're new to this, it will take you a little bit of time to go ahead and master this, but trust me, this is just as easy as anything else, right? So, yep, thanks a lot. Hope you enjoyed this video. See you in the next one.